Okay, welcome back. And today's our lecture is on compression members. Compression member or columns are structural members in a building that take loads in compression only. So, in this lecture, I have to give an overview about a column, a compression member. Okay, for example, you should know that we in reinforced concrete structure we have a composite column. It may have steel and concrete as well. In steel, we have a pure steel column, or it may be a composite column, a W section. For example, I can have a column like a W section, like this. This is a W section, and for example, this rectangular section, and you have poured the concrete here, and this is filled with concrete here. So this would be a composite construction, or it may be a plain column, anything. Okay, for the first time, the failure a column is actually you have to design column on its yielding its limit state. Limit state mean that it's on its failure state. So for the first time, uh, a scientist whose name was Leonard Euler gave his equation about column. He used simple mathematics, and actually he asserted that a column may buckle or fail under critical loading. For example, he told us that if you have a column and if you apply a compressive load P that is applied concentrically, that if it is applied and if it is increased gradually, then a column will fail or buckle. Buckle means that it will be like this. The column may buckle under this load. And he defined this load P as P critical because it's a critical value. And he has actually derived it. And the value of this P critical load was found to be pi square EI divided by L square. Now you should know that E is the modulus of elasticity, and for steel it is 29,000 ksi. I is actually area moment of inertia or second area moment. And for example, if you have a column, for example this is steel column, and you have this as B and this is D, then I would be equal to BD cubed by 12. And similarly, for circular section it is pi d4 by 64. So it can be found out. L is the length of a column. Okay, now again from this equation, now this is the P critical or the load at which a column will buckle, tend to buckle. Using this equation, you know that what is stress. I mean the load can be converted into stress, and you know stress is equal to P by A. Now I have this P critical at as pi square EI divided by L square, and if I divide both sides by A, that is area of cross section of a column, then this would be referred as stress critical, or I can use F critical. This is stress because load per unit area is stress. Now this I can be shifted here. I'm arranging this. So this will become pi square E divided by L square A by AI. A by I. And from your knowledge, you know that radius of gyration is equal to under root I by A. It is equal to, for example, R is equal to I by A. Now squaring both sides, you will get R square is equal to I by A. It means A by I would be equal to 1 by R square A by I. So this is equal to R square. This is equal to R square. This is equal to R square. So I can rearrange it as F critical is equal to pi square E divided by, now this can be L by R, and whole square, because this is square as well, and this is equal to R square. So it's very easy. You can rearrange it. I should do it again for you as well, because stress critical would be equal to pi square E uh, L square A by I. Now A by I is equal to this 1 by R square. Now you should know that this is slenderness ratio, and slenderness ratio highly depends upon the support conditions. For example, if two sides of a column are hinged, then the value of K would be equal to 1. So I can multiply K here. So I may multiply here and I put whole square on it. Now this would be the F critical, or the stress at which a column tend to buckles. A column buckles under a compressive load. So first I have found P critical, at a load at which column buckles, and from this I have simply found out the critical stress. Okay, next, scientists later realized that column not only fails in buckling, but it may also fail in yielding of material. For example, I have a column, and this column is short column. For example, it is 24 inches. And this short column is called strut or short column simply. And you may have a long column as well. And both are subjected to a compressive load P. Now, this column is very long. Its slenderness ratio is large as well. You may find L by R or KL by R. It would be large enough. And it tends to fail under buckling because it is unstable. Slenderness ratio is very high and very large. So column may buckle. But this column is very stable. It is short column, it is strut. So this column may not fail in buckling. There would be another mode of failure for this, and that would be material failure. So for a column we have got two types of failure. Number one, a column buckles or under compressive load, or it may yield, the material may yield. And why material yields? Because when the steel was formed, when the steel section was being prepared in the industry, residual stresses were developing in that section, and as a result steel has already yielded its Fy value. It is somewhere here. That's why material gets yield under load. So this is a very sensitive science, and that may be explained later. But for the time being, you should know that there are two modes of failure for a column. Either it fails by buckling, or materials may fail. For example, how to find that a column fails by its material failure, or it tends to fail by its buckling? This is geometric failure, and geometric failure is actually related to buckling of a column. And this material failure is related to a material failure. The steel has reached its Fy value. So how to find that a column is whether failing due to its material failure or geometric failure, that is due to buckling? So I have a simple formula. I'll find this value. This is a boundary condition. 4.71 E by Fy. Now E is the modulus of elasticity of steel. For example, it is 29,000, and this is for A36. It is, for example, 36 KSI. So I'll find this value, and I'll find my slenderness ratio for both the columns. And if the slenderness ratio is here, it is lesser than this equation, lesser than. So if KL by, you have plotted KL by R here, and this is your yield stress. Now KL by R is here, somewhere here. It means your column will have a material failure, and you will use this equation, F critical that is the F critical, a critical stress equation would be used as this. And what if your KL by R value you have found, because you have the K value, this is due to support condition, this is length of column, this is radius of gyration, this is from the manual, and it comes out to be greater than 4.7 E by Fy, then you are somewhere here in this region, and you will use F critical or stress critical equal to this, where Fe is the effective stress. It means when you are here in this region, you are in the squash region. You are using a squash equation, and this is the squash equation. It should be very clear to you. If your KL by R value is somewhere here, I mean your KL by R value is lesser than 4.71 E by Fy, it means you are using a squash equation, or you will use a squash equation for design, and that would be equal to F critical is equal to 0.658 power Fy divided by Fe into Fy. This is F effective. Okay, what if your KL by R value is greater than 4.71 E by Fy? Then you will be here. This is Euler region, and you will use this equation for computing critical stress. Now, okay, this is squash region, or in other words, you may say it is an inelastic buckling. And if you are here, I mean your KL by R value is greater than this 4.71 E by Fy, it is also called lambda R, then you have elastic buckling in your column, because inelastic buckling means the material has failed due to material failure, and elastic buckling means the column has failed due to buckling, due to geometry. So they are alternative, the words are used invariably. I mean, sometimes you may use material failure, it means you have inelastic buckling. If you have a geometric failure, it means you have elastic buckling. Here KL by R should be less than lambda R, and lambda R is, you know, this. Here KL by R is greater than lambda R. So this region is squash region. Squash, you will use squash equation. Here you will use Euler equation. So summary is, a column may fail according to Euler equation. A column may fail according to Euler equation, and in this case a column may fail due to buckling or according to Euler equation. Then in that case F critical would be this. It means KL by R is greater than lambda R. Okay, a column may fail due to material failure. In that case KL by R would be less than lambda R, and that would be governed by using squash equation, and squash equation is this one. So it's very simple. If I solve a numerical on it, it would be very easy. So you should be well versed that these are the all related things. For example, finally I want to give a last note on this, that inelastic buckling, squash region or squash equation, and material failure, or KL by R is less than the equal to 4.71 E by Fy are all one at the same thing. Okay, again, elastic buckling or Euler failure or geometric failure or KL by R is greater than 4.71 E by Fy, they are all one at the same thing. So it is very easy, very conceptual. Just give it a time and you will understand it. Here, okay, I can also use, and also this thing. This is Euler equation for computing critical stress. Okay, and let me highlight this into red for you understanding. So all red highlighted things are 1 at the same thing. 1, 2, 3, 4, 5. And this 1, 2, 3, 4, 5. They are all same things. Okay, let me solve a numerical on it. It's a very simple numerical. It's a W1033 section. It's a W1033 section. So W1033 section means it has been made or fabricated into a column like this. So it's a column. So you have its length. Okay, length is given 20 feet and A992 steel. It means its yield stress is 50 ksi. Again, it's a W10 into 33. Now I have to find out whether it will fail due to yielding first or it would buckle first. So it's very simple. It's a very preliminary question and it's very simple. I'll find the critical load at which column buckles. So I'll use Euler equation. So I've used this and I have pi as 3.14159 E, 29,000 ksi. I given to me all from the manual. You go to manual and find I. And this is length because this is inches. So this 20 feet has to be converted into inches. So I've multiplied it with 12 and I've got square of it and I've got this. Okay, at what load a material yields? The yielding criteria say P is equal to FyAg. So Fy is 50 for A992 steel. Fy is 50 ksi. The gross area is from the manual. Now this gross area, this I value, these both should be taken from the manual. So you should go to manual and find I and gross area for W10 into 33. Okay, I've multiplied it with 9.71 and I get 486 kip. Okay, you see that P critical value is 182 kips and yielding value is 486 kips. It means at the low, when a column is subjected to compressive load P, and when P reaches to 182 kip, it would buckle. As 182 kip is less than 486 kip, it means column will buckle first because the buckling load is reached first and yielding load is reaching later. It means column is going to buckle first. So it's very easy. Okay, next I have a question that this is again a W section. The length is given. A992 steel is given. It means Fy is equal to 50 ksi. Available column strength. I have to find the available column strength. So from the manual I have gone to W12 into 79. I'll go to manual. I'll find the radius of gyration, that would be the minimum of it. You may have Rx and Ry. Value of E would always remain same, 29,000 ksi. You should memorize it. The value of K is equal to 1. Now K is 1 means both sides are hinged. So both sides are hinged, so K value of K would be 1. Sometimes what if one side is hinged and the other is fixed, and K value is about 0.7. So it can be found out from the table. The table is, I'll tell you where in the book the table is, but you can go to Sagwai book and you find that table. The gross area is again from the manual, W12 into 79. So I have to find the strength of a column. Okay, first of all, you should know that I'll have to find this KL by R value. Again, this is actually lambda R. You must remember KL by R. Now K is 1 because both sides are hinged. Length of column is 10 and I'm multiplying it with 12. To convert it into inches, the value of R is 3.05 from the manual. This is RY. So you should find this value from the manual. And it comes out to be 39.3. It's the less than 200. This is actually the checked for slenderness ratio, the required limit for slenderness ratio for columns. So it should be less than 200. For tension member, the slenderness ratio limit was L by R should be less than 300. I remember. For column it is 200. Okay, I found out KL by R. So next this is slenderness ratio actually. So lambda r value is equal to 4.71 E by Fy. Fy is 50, E is 29,000, and my lambda r value is 113. It means my KL by R value is less than 39.3. Means my KL 39.3 is less than 113. Remember, this is lambda R. Remember, this is KL by R. Now when your KL by R is less than lambda R, go back. I'll go back. This is lambda R. I am lying somewhere here. It means inelastic buckling. It means squash equation. It means material failure. It means this. It means I have to use this value, F critical. Okay, what if, again I have to, what if my KL by R value was greater than my K, I should change the pen. Okay, what if my KL by R value was greater than lambda R, 113. The value was found out to be 113 for lambda R. Then I would be here. I'll be using elastic buckling equation. I'll be using Euler equation. I'll be using this value. It means the failure would be geometric. In this case, I have KL by R values less than lambda R. My KL by value is less than lambda R. KL by R is 39.3 and lambda R is 113. Going back again, I want to reiterate it so that you can easily understand this. Okay, KL by R is less than lambda. This is lambda R. So KL by R is less than lambda R. I am somewhere here. It means squash region. It means I have to use this equation. It means it's a material failure. It means this and this. Yes, this is my case, 39.3, and this was found out to be 113. Next, I think it should be very well understood. So that's why I have used this squash equation. I'll call it a squash equation for computing critical stress. Okay, this is multiply sign. Okay, finally Fy 50 ksi. Effective stress I have computed from 185, and it has been computed from I failed to compute it, but this effective stress would be easily computed from, you can see here, this, you can compute effective stress using this formula. Pi square E divided by the slenderness ratio. It means here 185, effective stress would be computed using this formula. $29,000, and slenderness ratio is 39.3. You compute it, and you will compute it, and you will get this value, 185. Okay, finally, you should know that this should be square. So it comes out to be 185. I haven't written here, probably I've missed it, but you can easily find this effective stress. This is very easy to found out. You will use this formula, pi square E divided by KL by R square. 50 into so you have got this critical stress. This critical stress can be converted into critical load. This is the stress at which column will fail, and you know that it would be a material failure. So multiplying it with the gross area, this is from the manual, 23.2, further it is 12 into 79. Go to manual and you will find this. So this is the load at which a column will fail, and for LRFD you have to multiply it with the 0.9. This is factors for column, and for AST you have to divide by 1.67. so make sure 1.67 multiplied by 0.9 gives us 1.5. so this is the load for LRFD, this is the load for 623 quips for ASD at which column fails, and the mode of failure is material failure. Okay, next question is very easy as well, and I want you to do it on your own. I want you people to do this. This is 10 into 49. Actually the column is cross section is given like this, and this is X and this is Y. Support conditions are different, so that's why two values of K's are used. Kx equal to 1, it means both sides are hinged there, and this is 0.7. Your support conditions are defined here. So you'll find two slenderness ratio based on your K value and based on your radius of gyration. So you will have to take the minimum of this both two. You have to maximize the slenderness ratio. You have to take the maximum of it. I have written here that slenderness ratio in Y is controlling because this is maximum. So this is very easy. You have to find the slenderness ratio along x-axis and y-axis, and you have to take the maximum of these two. And again you have to solve again the whole question. Again slenderness ratio in Y is less than lambda r. It means this is going to be in the squashed region, and the failure would be material failure. So I have written it, material failure. And again I've found out this F effective, and again you have to use the squash equation, and we have solved it. The only point or only twist is two slenderness ratios based on two support conditions along x and y axis. So the point is you have to select the maximum of slenderness ratio. This is very important point. So why you are using the maximum slenderness ratio? Because you have to reduce the effective stress. You have to find the lowest value of the load or stresses. So that's why if this value is greater, then this would be reducing. So this is very easy. You can think over it and you will come to know. You can ask as many questions as you can. Next I'll solve more questions. I have a question here, so you will understand more. I'll solve it in the next class, but for the time being you should know the basics about the column failures. You should know the basic equation. The equation is Euler equation. This is very important. How to compute critical stress? It is very easy. I have divided. This is not I here because I have shifted here. You have computed the critical stress from the critical load. Then you should know that a column may also fail, may have a material failure. Means KL by R ratio is slenderness ratio is less than lambda R. It means you have to use the squash equation, and this is squash equation. It means it's a material failure. It means it's inelastic buckling. Okay, next KL by R may be greater than 4.71 E by Fy. It means it would be a geometric failure. It would be Euler failure. I'll be using Euler equation, which is this or this. It means it's elastic buckling. So this is the second mode of failure. In black I have a first mode of failure, that is material failure, and this is geometric or buckling failure. I've solved this question very easily. This is very easy question, so you need not worry about it. This is very basic. Yes, this is a bit complex, but not that complex. It can be easily solved. I have solved it out. So the only twist is F effective. So F effective can be found out using this equation. F effective, you should remember, is always equal to pi square E divided by slenderness ratio square. Means pi square E divided by KL by R whole square. I found out here. So best of luck. I want you to go through this lecture very keenly, and you should take interest in this, because this serves as the basic for the design of plate girders. So in coming lectures we have to study plate girders, but you should have the idea about some critical boundary values, lambda r 4.7 e by fy. What is e? What is fy? What is radius of gyration I by a? What is critical load? What is critical stress? What is Cauchy equation? So everything is very easy. Just go through it. Thank you very much.